Today I'm going to talk to you about voltaic cells and the standard electrode potential, and you can find this information in chapter 18 in your textbook. All right, so first let's just go over some terminology so that it's clear what I'm talking about as we go through these different concepts. So first is electrical current. An electrical current is just the flow of electrical charge, and this could be either electrons flowing through a wire or it could be ions flowing through a solution, and both of those are forms of electrical current. Okay. So the next one I'm going to talk about is an electrochemical cell, and that's what we're going to focus on mostly in this chapter. And an electrochemical cell is just a device where we use a redox reaction to generate electricity. So all of the redox reactions that we've just learned about, we're going to apply them to their use in electrochemical cells. Okay, a voltaic cell or a galvanic cell, they're the same thing, and they are electrochemical cells that produce electrical current by using a spontaneous or thermodynamically favored chemical reaction. Okay, and that's what we're going to talk about for most of the rest of this lesson, but there is also another kind, and the second type of electrochemical cell is called an electrolytic cell. And an electrolytic cell consumes current so that it can drive a reaction that is not thermodynamically favorable. So it essentially takes things in the opposite direction. And probably the version of this you're most familiar with is when you do electrolysis with water to generate hydrogen gas and oxygen gas. That reaction doesn't happen spontaneously on its own. You have to put electrical current in to make that happen. Okay, and now half cell is it is one of the two portions of an electrochemical cell, and it's either where the where the reduction happens or where the oxidation happens. So this is where one of the half reactions that we talked about in the last lesson, this is where one of those occurs. Okay, and then an electrode is a strip of metal, it's a conductive surface through which the electrons can either enter or exit the half cell. All right, and as I get to the diagram on the next slide, a lot of this will make a little bit more sense. Okay, so let's go through some of these things we just talked about. So the electrodes in this case would be the manganese solid that's over here on the left and the nickel solid that's over here on the right. Those would be our two electrodes. The two different beakers are our two half cells. So in one of them, the reduction reaction takes place, and then the other one, the oxidation takes place. And two other terms that you need to know are cathode. So one of the half cells is the cathode, and the other half cell is the anode. All right, and oxidation always happens at the anode. Okay, so sometimes we use the phrase, I guess, anox, to represent the anode, because that's where oxidation happens, and red cat is often used to tell you that the cathode is where reduction takes place. Okay, so you just need to keep those straight. And then the salt bridge is the last thing that's labeled here on our diagram, and the salt bridge just allows charge to remain neutral in our two half cells, or else the reactions aren't going to happen if we get a buildup of positive charge in one and negative charge in the other. And the reason that would happen is because we're moving electrodes from the anode to the cathode, and so when that happens, we're going to get a buildup of negative charge at the cathode and a buildup of positive charge at the anode. The salt bridge just has ions in it, positive and negative ions. It could be any salt that's not going to participate in the reaction, and then the little plugs here at the end are semi-permeable, and so what that means, they're usually made of glass wool, and that means the ions can move freely back and forth between the salt bridge and the half cell. Okay, and then here I just have a question just to make you think a little bit about what's going on. So why do electrons always flow from the anode to the cathode? And that's because oxidation at the anode results in a loss of electrons. So you have electrons being produced there, and then they travel through the wire over to the cathode where they're being used up. So they're chemicals you have on the right side at the cathode are being reduced, and therefore they are gaining electrons. So they always flow in just that direction, and that's how we can control where the electrons are flowing and use this to generate electricity. All right, the next thing I want to go into is talking about how we know which direction the electrons are going to flow. But first, just a little housekeeping sort of thing. There's a different notation you can use to write these reactions, and so I just want to show you that really quickly. I'm probably not going to ask you to write them this way, but they will sometimes be written this way in questions on the AP exam, so I want you to have some idea what they mean. So if we're considering a reaction that's copper 2 plus zinc solid, and that's going to copper solid plus zinc 2 plus. The way we write this is we first put the oxidation half reaction on the left side, all right, and that's just going to be zinc solid going to being oxidized to become zinc 2 plus, okay, and then we just write those with just one single line between them. And then on the right side, we write the reduction reaction, which is just the copper 2 plus going to copper solid. And again, we just separate those with a line. And then in the middle, we put 2 lines, and that represents the salt bridge that connects those two half reactions. Okay, so this notation here represents the electrochemical cell that's shown below, where you have zinc being oxidized and copper being reduced. Okay? All right, now let's get into how we can tell which direction the electrons are going to flow. So if you remember, one of the things we've talked about multiple times throughout this year is that the universe always tends to want to move toward a state of lower potential energy. And so there's some potential energy associated with both the zinc and the zinc 2 plus and the copper 2 plus and the copper. And so if we make a comparison between those potential energies, the potential energy difference, that will tell us what the potential difference is for this particular cell. Okay, and we usually express that in units of joules per unit of charge, so per electron that's being transferred, okay? So it's going to be different if we are transferring 2 electrons like we are in this case, or if we were transferring 6 electrons, that would be a different potential difference because of more electrons being moved, okay? And then the standard cell potential is going to just be the potential difference between the 2 electrodes at under standard conditions. And so those standard conditions, just as a refresher, are 25 degrees Celsius, 1 molar concentration, and if we had gases, 1 atmosphere pressure for the gas. All right, and the moving back and forth of those electrons, that potential difference gives us some amount of force that can result, and we call that an electromotive force. So the potential difference gives rise to a force that results in the movement of electrons, and so that's why it's an meaning electron, motive, moving force. So how much force does this reaction give us to move electrons? Now, to find this potential energy difference, we need to know what the electrode potential is for a given half reaction. And so we call that individual half cell potential the standard electrode potential. Okay, and then in addition to that, we have a standard hydrogen electrode, which is just H plus gaining 2 electrons to become H2. And we because all of these are relative values, we have decided to set that value as 0. So everything is compared to that standard electrode. And then when we're comparing the standard electrode potentials for different half reactions, we do the cathode minus the anode, okay, because the cathode is where everything ends up, and we usually do final minus initial. And when we compare those, if we get a positive value, then the reaction is product favored, and if it's a negative value, then the reaction would be reactant favored. Okay, so you're going to want to sort of keep those values in mind, but we're going to do an example that will hopefully make this a little more concrete. Now let's do an example, and the example I've given here is actually a little bit difficult, but I'm just going to walk you through it, and you can hope that know that the ones that I'll give you in Mastering Chemistry should be a little easier in terms of determining what the equation is. Okay, so a lead acid battery is rechargeable, and they're commonly used in automobiles, so these are usually car batteries. Answer the following questions if the battery consists of lead and lead 4 oxide electrodes separated by a porous membrane in a solution of sulfuric acid. Okay, so we know that our two electrodes are lead and the lead 4 oxide, PbO2. And so what we need to do is go to our table of standard electrode potentials and find the equations that show us, or the half reactions that show us how those things can act as either things that are reduced or oxidized in the presence of sulfuric acid. So if we do that, the two half reactions that we find are Pb solid plus SO4 2 minus aqueous goes to PbSO4 solid plus 2 electrons. Okay, it's important to note that I switched this reaction the other way. They're all written as reduction reactions, but in this case, lead solid is actually being oxidized, and so I have to write the reaction the other direction. We still take the E as the same value. So our E for that reaction is negative 0.36. Okay, and then the second half reaction is going to be PbO2 solid plus 4H plus aqueous plus 2SO4 2 minus aqueous plus 2 electrons is going to yield PbSO4 solid plus 2H2O liquid. Okay, and the cell potential for that one is going to be 1.69. Okay, so to get the balanced equation for the reaction, we just add the two together. So it's going to be Pb solid plus PbO2 solid plus 3SO4 2 minus aqueous plus 4H plus aqueous goes to 2 PbSO4 solid plus 2H2O liquid. Okay, so that looks like a long, complicated reaction, but really all I did was find the two electrodes in our standard electrode potential table. And that's on page 873 on your book, or some of them, for example, the first one here is not in that table because it's an abbreviated list, but you can find it in Appendix 2 in the back of your book. And on the AP test, I should note, they used to give you a table of these, but they don't even do that anymore. They just give you the values that you need to do the problem. So you wouldn't even have to go through that process. They would give you the ones you need. All right, so which electrode is the anode and which is the cathode? So I already told you that the lead here is being oxidized, so that is going to be our anode, and that makes the PbO2, which is reduced, the cathode. Okay, so in this case we have lead going from solid lead to Pb2 plus, and we have lead 4, Pb4 plus, going to lead 2, which is Pb2 plus. Okay, so now we want to calculate our E cell. We want to do anode minus cathode, and I've already got the numbers up here, so we want to do 1.69 minus a negative 0.36. Okay, so minus a negative means we're going to add that number, so that's going to give us 2.05 volts. Right, so this is definitely going to be a thermodynamically favored reaction, and we're going to talk about how we can do calculations with that and relate it to delta G and the equilibrium constant in the next lesson.